Hey everyone, and welcome to another challenge write-up video. This is UCTF Sandbox. It was a pretty fun challenge where we're going to have to escape out of a sandbox written using the Unicorn library. Unfortunately, I didn't solve this one during the CTF. I saw that it was using the Unicorn library, and I just don't know much about it, and there were so many other fun challenges to play. I played those other challenges instead, but now that the CTF is over, I've gone back and read some of the write-ups. It is a very fun challenge. Still a pretty difficult challenge. I don't know if I would have been able to solve it during the CTF, but thankfully there's great write-ups, and they were able to provide lots of pointers as I got stuck. So the three write-ups that I'm referring to are the official write-up by the UCTF authors, and they give a couple paragraphs describing the intended solution. There's a really good write-up by Nobody is Nobody, and they go into a lot of depth. They talk about all the different bugs, the different gadgets. If you're a person that prefers written version over video, I highly recommend checking this out. This is the best write-up by far. They talk about everything. They go through the disassembly, and they lay out their plan, and they give their exploit script. So amazing write-up. There's also one by Zero, who also gives their solve script. It's fun. These two people actually did different solutions, and we'll talk about the two different solutions a little bit later, but both very cool. So the outline for the rest of the video, first we're going to look at the Unicorn library and see how it works normally and get kind of a sense and a feel for it. Then we're going to load the two binaries in Ghidra and find the respective bugs in both of the binaries. And then last we'll look at the exploit script. And there are three different stages to the exploit script. We're going to look at the info leak. We're going to overwrite this syscall whitelist, and then we're going to pop shell. So yeah, let's get started. Like I said, the Unicorn, if you go to their homepage, they have a lot of good information. They call themselves the ultimate CPU emulator, but really what helped me understand was just going quickly over this tutorial they have in C. So they give this example program and they show how to compile it, and they talk about what all the lines of code are doing. So I think just very quickly going over this kind of helps set the context for what we're going to be breaking out of. So this is that code. I just copied it over here. I think the syntax highlighting here is a little bit better. But in the example they give, they're going to be emulating these two assembly instructions, this increment ECX and decrement EDX. And we can see this is the hex code for it. And so it's just those two calls, and so the rest of the code is just to set up the fake CPU so that it'll execute those two assembly instructions. So there's like this UC open, which is how I guess the Unicorn engine starts, and you pass it this UC engine object. And you also specify the architecture and the mode. So I think the Unicorn engine supports like a whole bunch of different architectures and stuff. I think it's why it's such a popular library to use. I see it all over the place. There's this is how you can map in memory. So they're mapping in 2 megabytes, which is pretty cool. You can specify the protections. Then you can write to the registers. So this is all before anything has really started. We're just doing setup code right now. You can set up, so we're setting up registers. We're going to set the value of ECX and EDX to some initial values. I think the values are up here. Yeah, 1, 2, 3, 4, and 7, 8, 9, 0. And then you start emulating. And so this is going to execute those two assembly instructions. And then at the very end, we can inspect the state of the CPU. So I think I was confused when I first played with this challenge. So I played with it a little bit during the CTF. I did the buffer overflow, which we'll see in a second. And afterwards, nothing happened. Like I expected GDB to stop when it did the buffer overflow. And I should have thought more about it. Like I thought that Unicorn was going to just kind of map the binary into some process space and start executing from there. But that's not actually what Unicorn does. Like Unicorn, like it's a full virtual CPU, and I believe it reads in those assembly instructions, and it's not executing it on the real CPU. It's just taking it and saying, oh, this is a call to EDX. Increment EDX. I'm going to increment the variable that I used to store EDX. So it's like re-implementing everything the CPU does. And so that's why my initial buffer overflow wasn't doing anything, because it's not actually overflowing anything. I mean, it is overflowing something, but that's all in like, a virtual space, not in, the real CPU memory space. So as mentioned, we're given two different binaries, the hello and loader. If we load the hello binary in Ghidra, this is what we get. Nice and simple. It's going to define a 256 byte buffer. It's going to do a gets on that buffer and then a printf on that buffer. We can see just classic buffer overflow on the gets buffer. If we do a checksec on it, so checksec file is equal to hello, we can see lots of goodies. So no canary, just a buffer overflow. We're not going to be doing shellcode, but there's also no pi. So basically we have a easy place to do as much wrapping as we want. And so like I said, this binary is going to be loaded by the loader binary. So if we take a look at that, this binary was huge. I think it was like 34 megabytes of a lot of stuff to disassemble. I guess the Unicorn library is statically linked in, which is why this is so big. But let's take a look at the main function. Yeah, there's a lot to it. Unfortunately, it's my understanding that the Unicorn library doesn't provide a way to directly load in ELF binaries. You have to do that yourself. And so most of what this code is actually doing is just setting up the Unicorn engine with that given ELF. And so it's going to set up the stack, it needs to set up registers. There's the different calling conventions, like it's going to load in the different arguments depending on how you call it. So a lot of that sort of stuff, most of the interesting stuff doesn't really happen until a little bit later. And I think just the only two really interesting things are that they hook into two different functions. There's one for hooking syscalls and one for hooking invalid memory. So if we do an out-of-bounds memory, this is what I was seeing during the CTF when I just tried a naive buffer overflow and then I gave up. It says, missing memory is being read or missing memory is being written or write at. And so it's cool that Unicorn can tell you when you're doing an out-of-bounds read or an out-of-bounds write, and you can just hook directly into it with the function. As far as I know, there's no bugs in there. Instead, if we look at the next function, the next of the two interesting functions, this hook syscall function, what's cool is whenever that vulnerable binary makes a syscall, it'll call this callback within the the loader binary, and it'll check and actually implement the syscalls here. And so all the bugs that exist are in this function, and this is really what the exploitation is about, is actually exploiting this code. So I've cleaned it up slightly. There's a lot more we could do. I'm just going to zoom in on a couple of the different bugs that are interesting. At the top, the challenge author was nice enough to put this at the top, and it looks very fishy. So what's going to happen is this syscall handler is going to read our registers that are, the registers from the vulnerable binary, and it's going to read out RAX, RDI, RSI, and RDX. It doesn't give you these by default. To actually find what these values are, it's reading this. Normally this would be, like where's the registers? It'd be a constant like this, but this gets stripped out. So to actually find these, what I ended up doing was I just copied this. I did a git clone of the Unicorn library engine, and then from here you can kind of go through. I built it, and this is for .NET. You can see these mappings. So 22 is ECX, and so you can just kind of go back and forth. You hover, you see, oh, this is 35, so you go down to 35. 35 is RAX. Just quick tip if you get stuck with these values. But anyways, so it's going to read RAX, RDI, RSI, and RDX, and then it's going to see what RAX is. So if you remember from our calling conventions, when you do a syscall, RAX is the one that holds what syscall you want to do. As far as I know, there is no 400 or 2000 syscall. Like if we go to the syscall docs, we scroll all the way down. The last syscall is 332, so definitely not a real syscall. So the challenge author was nice, and it's a very strange syscall, and the disassembly doesn't do the best job out of it. But basically, it gives us a relative write on the stack, and it'll write the number of syscalls that have been called so far. And a very strange gadget, but it's all we really need. If we pair that with another syscall, so this is the syscall handler for when none of these other syscalls matched. I think there's handlers for maybe like 5 or 6 syscalls. So if none of the other syscalls match, so if RAX doesn't match any of the other handlers, there's one at the very end where it'll check and make sure see if it matches one of the exit syscalls. So by default, the exit syscalls, there's 2 of them. There's this 3C and E7. So if we look at these those syscalls, would we say E3 is one of them? Or 3C? OX3C? So this is just the exit syscall. So it's saying, if it's, and the other one I think is the exit group or something like that. So it's saying, if it matches one of these, we're allowed to do that syscall. And when it does this syscall, this is like the actual running process. Like it'll just execute that raw syscall. So this will just exit the binary. But we can see what's interesting. They're kind of hinting here. It's going to call syscall with the syscall number, but it's also going to pass RDI, RSI, and RDX, and these are the ones from our vulnerable binary. So if exit syscalls had more syscalls that were interesting, we could directly call whatever we want. So cool. So we can chain these two bugs together. So what if, if we look at the binary, exit syscalls is actually in a memory segment that's readable and writable. So up here, we have a gadget to write somewhere, and over here we have our whitelist. So if we put them together, we're going to use this gadget, this RAX equals OX4000. We're going to overwrite the exit syscalls so that it contains exec CVE, and from there then we can just call bin shell. So that's the game plan, and that's pretty much what we do. There's one other bug we have to do, and we need an info leak. Thankfully, this code's kind of nasty, but basically what's going to happen is you can ask for it to read, like doing the read syscall, and you'll ask it to read from standard in. It's going to allocate a buffer based off of the size you give it, but when it does that read, like let's say in the example we're going to have it read OX600 bytes. When it does that, we only send it, I actually send it 0 bytes or 1 byte for a new line, and we'll get all that default memory, which is just stack space, because it's not cleared. And so because of that, we can then read those variables. So in the vulnerable binary, we're going to tell the parent binary, hey, like I want to do this read syscall, and I want you to read from standard in, and it's going to be a buffer of I forget what is 6, a couple kilobytes. The host process is going to be like, sure, it's going to do the read syscall. It's going to allocate first it's going to allocate that big buffer. It's going to do the syscall, and then it's going to pass that syscall back to the child process. But since we're only passing 1 byte, we're going to get all that uninitialized stack variables data, and from there we can just start plucking values that we think are interesting. So we're doing this in like ROP sort of, we're still ROPing. So it's a little bit hard to like kind of parse gadgets and stuff and parse what we got as a response. So we're then going to use this syscall, this RAX equals 1, to, I think it's supposed to be a write gadget, but what we're going to be using it for, so you can read a memory address, it stores it to RDX, and then it's going to, whatever OX23 is, what is OX23, 35, so it's going to write it to RAX. So it's going to read a memory address and then store it to RAX, but more importantly, it actually prints it out here. So with all of that, we kind of have our game plan. So first thing we're going to do is that info leak. So we're in the challenge binary, the vulnerable binary, and we're going to say, hey, the parent process, I want to do a read syscall. I want to read from standard in, and I want to read, a very large buffer. But then, so the parent process is going to allocate a large buffer on the stack, but we're only going to pass it like, a couple of bytes. So the parent process is going to pass back to the child process all this uninitialized memory. And from there, we can start looking for gadgets, for info leaks. We can't directly read those values. So instead, what we're going to be doing, because we're still wrapping, instead we're going to then use this RAX is equal to 1 syscall, and it's going to read in the child memory space and print it out. And so when it prints out that uninitialized memory for us, we can take that and we have our info leaks, and we only need one info leak, which is libc. And we need the libc leak for, which we'll talk about now. Eventually we want to call that exec CVE call. And so to do that, normally that call would be whitelisted, but we're going to use this syscall, the RAX is equal to OX400. We're going to do that relative write with this syscall count. So we're going to set this to 59 by making 59 fake syscalls. It's going to write to the exit syscalls variable, and we're going to place in the number 59, which is the exec CVE syscall. Cool. And then we make the exec CVE syscall. We have to pass bin shell. We can't do pass bin shell in the child process because we don't know where that. Technically, it's mapped somewhere in process space, but it's not really a known address. Like you could calculate the offset. It's easier just to leak libc and find the bin shell within libc because we know that's going to exist in the parent process. So then, but now that exec CVE is a allowed syscall, we're just going to call exec CVE, and it's going to forward all these registers for us. So at that point, we'll have shell. So yeah, let's look at the solve script. Sweet. So this is the solve script. Very standard sort of pwn tool solve script. We're going to load in the hello elf, the libc, I grabbed the libc by starting up an Ubuntu 2004 box and then just copying out the libc file into my local directory. And the challenge was running on 2004. Then we're going to start the process. We have to find the offset. I found this offset in a different script. I wrote here, solve hello. So this is very standard for figuring out what offset you need to do the buffer overflow on. Basically, we'll get rid of this, we'll get rid of this. You just do this p sendline pwn cyclic 1000, and then you read in GDB what character offset actually is being popped off the stack and set to RIP. We can take a look at what this looks like. Python 3 solve hello.py. Continue. So we sent a whole bunch of text. Now somewhere in here, the buffer overflow is going to start, and like maybe like right here, this is the value that's going to be popped off of the stack and set to RIP. We're just trying to figure out what value that is. And so if we look, it's really messy because it's so big, but we can see this is the next value that would have been popped off the stack and set into RIP. But the GDB is like, nah, I'm not going to, or the process is like, nah, this is not valid, memory address to execute from, so it doesn't. So it gets stuck here. But we then know if we were to put something exciting there, like, if we were to go back, the offset was this. If we were to then do a times offset plus oxo pwn.p64 ox deadbeef, since we know offset is the very end, we should be able to execute this. Oh, p64, whoops. Strange. And we continue, and we can see, hey, I'm not going to execute address deadbeef. So quick little way to figure out the offset. Very cool tool. Anyway, so we found the offset. Then we're going to set some variables. So this is the data segment of the hello binary. And this is important because it's a read-write segment. And so that way, when we copy over that uninitialized memory, we're going to place it here. There's this RBP, which we're not using anymore. There's this syscall gadget, so we need something in the hello binary that does syscall ret. And to find this, you can use wropper. So we'll do wropper file is equal to hello. This is all the ROP gadgets, and we can see here's a syscall ret gadget. So we just copy this over, and I'm pretty sure that's the one I was using. Yep. Sweet. So now we have a gadget that does syscalls, and the rest of the gadgets are loaded automatically through pwn tools. So we're going to start ropping. So this is how you rop in pwn tools. We're going to use pwn tools does this amazing thing where it'll find the pop gadgets for you. Keeps your code nice and clean. So I'm saying pwn tools, set RAX, RDI, and RSI and RDX based off of this. Just find the gadgets and do it. So cool. So RAX needs to be 0. So this is the syscall to do that read. So we can get that uninitialized memory. This is just setting the rest of the registers that the binary wanted. So here's the buffer that we're going to read into, or we're going to write the contents to. And this must be the file descriptor, and this is the size. And then we call that sysgadget. So once that uninitialized memory exists within the hello binary space, it's kind of hard. You can't really inspect it in GDB. I'm sure it exists somewhere, but we don't know where it really exists. It's some virtualized, emulated sort of process space. So it's easier. I just called that write syscall a whole bunch of times to find just addresses that looked interesting, because we're using that write syscall to actually get the juicy stuff. So to see what that looks like, let's do a pwn.interactive. Oh, this is how I do it. So like I said, I was doing like 90 to 100. So for these 10 times, I'm going to set REX equal to 1. So we're doing the write syscall. RDI is equal to 1. I guess, standard out maybe. I'd have to look back at the binary. But then RSI this is the variable we're going to read from. And this is how much. RDX is equal to 8. And then we call syscall. So it's just going to do this 10 times. And then at the very end, we're going to jump back to the start of main within the vulnerable binary so that we can keep doing this over and over. For our next, once we have our info leak, then we have to set the whitelist and everything. So we need multiple executions. So here we're going to send the exploit. So up to the offset, then we're going to start ropping. We're going to receive. This is the call that will, because we're doing that read syscall. We need to send it some data that'll fill that buffer, even though we're not filling the buffer because we want that uninitialized data. Then we're going to receive until buffer because, that's what we want for printing out these values. But instead, we're going to see what this actually looks like. So if we do python 3 solve.py, this is what those write syscalls looks like. So this is being printed out by the loader binary, and we can use this as our info leak. So we can see here's a 7F1C, so this is probably a libc leak, which is exactly what we need. So we'll copy this out and use that as the base for our, that is our libc leak. So let's go back, get rid of this. Was it 97? Let me just Control Z. Yeah, it was 97. Cool. So the next thing we need to do is we want to overwrite that syscall whitelist. Right now it only allows those 2 exit calls, but we want something more exciting. We want the 59th syscall. I keep referring to this page. I should probably call it out. It's a list of syscalls written by Chromium, I guess, but just beautiful. It's well organized. I use it all the time. But this is the one we want, exec CVE. And so we want to allow 59. Right now I think it allows 60. Yeah, so just an off by 1 error. We want 59 instead of 60. So to do that, we have to make, if we go back to Ghidra and see what it wanted. So we're going to be doing this syscall. Very strange, fake syscall where it's going to set this value to the number of syscalls that are being called. If we look at this value, it's being set up here. Every time we make a syscall, it's just incremented by 1. So we're going to do a bunch of no-op syscalls so that it's set to 59. I don't know I forget what it's set to originally. I guess right now it's at 11. So we've made 11 syscalls so far, and then we're going to make 48 more syscalls. So when we need to overwrite the exit syscall whitelist, we have to calculate the offset between this write and where that write is. To do that, I just break in that code block, and I just print out the difference, and then I set it here. So as an example, let's comment this out. We'll copy it. We'll place it here. Initially, I just set it to a value of 100. And then let's load it in GDB. We'll do Python 3 solve. Oop. So like I said, I break within that code segment. So this in Ghidra is right here. So I broke right here, and I'm just going to see what the current address it's currently writing to, and then I'm just going to increment or decrement RDI depending on whatever value it's currently set to. So currently we're right there. We're going to jump to where it actually does that overwrite, and we can see it looks like the overwrite is here, so it's going to write the contents of EAX into whatever RDX is pointing to. So we'll just jump to that line real quick, and we'll see what RDX is pointed to. So right now RDX is pointed to disassembler 2-byte opcodes. Not sure what that is, but cool. And we want to overwrite exit syscalls. Cool. So let's print out the address of exit syscalls. So that's that address, and we're currently writing into RDX. So what we're going to do is just copy this. So we're going to do print this minus this to see how far we need to go. We had it the wrong way, but if you do it the other way, obviously it would be positive. So it's 7820812. 7820812, which is what we have right here, minus 100 because we already set it to 100 right here. Yeah, that's how you calculate the value. So now we know that this is the relative offset between those 2 variables. Cool, and so when this loop is all done, it's going to set that exit syscall. One of its variables will be 59, and so now we can call bin shell. So we'll get rid of this. And the last thing we need to do is just call bin shell. We needed that libc leak so we could do a libc search bin shell and just figure out where that string exists within the normal libc space. And then from here, this is a very standard sort of wrapping. We'll just call exec CVE. We'll pass it to bin shell. We'll set both of these to null. We'll make the syscall, and it should just pass right through. And to show this works, the remote server is still live. Do I have any GDBs? Nope. Let's run it on remote. Python 3 solve. Nothing happens, which is what we want, and we get the flag, cat flag.txt. So UT flag, who needs WASM when you have QEMU? So pretty fun challenge. Just to recap, we broke out of a unicorn sandbox. We were given a challenge binary, which had a very vulnerable buffer overflow, and we were able to build a whole bunch of ROP chains. Using those ROP chains, we were able to call the syscall handler within our unicorn binary, and from there we were able to allocate some uninitialized memory and copy it back into the child process. Then we were able to use the write syscall to print out those variables so that we could parse them and get our libc leak. From there, we were able to do that weird kind of increment syscall counter till we got to 59, which is the syscall count for exec CVE. Then we were able to find that relative offset and do that relative overwrite to write that to our allowed exit syscall handler so that we can kind of smuggle our syscall through. And then we called, the normal syscall for executing bin shell, and we got shell. So overall, super cool challenge. Thanks to GGU for writing and UCTF for hosting, and I'll see you at the next CTF. Cheers.